In my last video, we learned that a matrix has a special kind of subspace called the null space. It turns out every matrix also has another type of subspace called a column space, which we're going to learn about next. Even though a null space, it took some effort to find it, it wasn't awfully difficult to end up getting that null space. Well, the good news is a column space is even easier than the null space, because the definition of a column space of any M by N matrix A, which will give it the shorthand COLA, just as the null was NULA. The column space of a matrix is just the set of all linear combinations of the columns of A. Another way to show that, let's say I have a matrix A which consists of a column vector, which I'll call A1. And next to that is a second column vector called A2. And we continue that until we end up at my last column, A sub n. So again, this is a matrix of column vectors. Then the column space of that matrix is just the span of all those vectors. A1, comma, A2, comma, all the way to AN. In the last video, we had a 2x3 matrix where we found the column space, that the null space ended up being the span of a single vector, 2, 1, 0. So again, in part 1 of section 4.2 video, we learned how to get that. Well, here's matrix A. What if I wanted the column space of matrix A? We're done. All we have to do is say the column space of A is the span of those three columns. So 1, -3, comma, -2, 6, -1, 5. And we're done. It's that friendly. Now, it turns out we're going to learn in future sections that the span of these three vectors is a little overkill. We could probably get rid of one of them for sure, maybe two of them, and we'll learn more about that later. But for now, if you just span all of the column vectors, you've got your column space. So let's notice something. Notice my null space has, it just happened to have a single vector. That's not as important as noticing what vector space did it come from. This vector is clearly from R3, where in my column space, my vectors are in R2. Null spaces and column spaces are subspaces of larger vector spaces. And it turns out you can stare at a matrix and you can see immediately that my column space must be a subspace of R2, where my null space has to do with the number of variables that we have. And so we can see that it would be a subspace of R3. Let's take a look at another example. Let's say we've got a set W of vectors of this particular form. So we have vectors in R3 made up of some combination of these A's and B's, and all we know that A and B are real numbers. Okay. So my ultimate question is, I would like to know, I want to find matrix A, whose column space looks like this. So that's eventually where we're going to head. So let's look at what we've got here. Looks like I've got a linear combination of some stuff going on here. So I think we could all see, if I could unscale the A's from these expressions, there would be left a 5 and a 1 and a -3. And let's unscale the B's, leaving -1, 2, and 0. So here's an easier way to see that this was just a linear combination of two column vectors. Well, that's what the column space is. So another way we could have stated the set W is it's just the span of those two vectors, 5, 1, -3, comma, -1, 2, 0. Well, it looks like we've got my matrix. The matrix is just those columns. And so my ultimate question is, can you find a matrix that satisfied that expression? And it looks like we've got ourselves a 3 by 2 matrix that made that happen. All right, let's try one more. Let's say I have a matrix A and I have a vector W. And I want to ask two questions. Is W in the null space of A? And is W in the column space of A? Well, right off the bat, let's recognize that my matrix A is a 3 by 3. And so the W vector, which is in R3, could theoretically belong to either one, based immediately just on the dimensions. So my answer so far is I don't know, but it could be true. So let's start with the null space. What should be true? What would answer this question? Is W in the null space? Well, the definition of a vector being in the null space is that it gets sent to the 0 vector after it gets transformed or multiplied by that matrix. So let's do that. Just the old-fashioned way. Let me set up a product of this matrix. I'll squeeze in this vector above the way we like to multiply, and let's go row by column. So let's multiply -16 added to -2, so I'm up to -18 plus +18. So far so good. Second row, 6 times 2 is 12, 4 times 1 is 4, 12 plus 4 is 16, minus 16. Then finally 8 plus 0 plus -8. Ding! Looks like we got it. So we verified by multiplying that W was sent to the 0 vector. So is W in the null space? The answer is yes. Real quick though, let's say I took matrix A and I row reduced it. Let's just check one more way we could determine if it's in the null space. So if we did this by hand or use technology, this is what my reduced row echelon form of A looks like. And what is this revealing? Like usual, we're calling out what are all the possible vectors that could be sent to the 0 vector. I've got one free at x3, which makes x1 negative 1x3, negative 1/2 x3. Unscaling that tells me we have any scaled version of negative 1, negative 1/2, and 1. So the question is W a scaled version of this? And I think you can see, if we were to replace x3 with a negative 2 and actually scale it, we do get positive 2, positive 1, and negative 2. So we've just checked it a second time. All right. The second question is W in the column space of A. What is that asking? Is W a linear combination of those 3 column vectors? And that takes me back to setting up a augmented matrix with A to the left, augmented with my target vector, 2, 1, negative 2. And again, if we row reduce this, we end up with this as my reduced matrix, and we can see just at this stage this is consistent, which just means we can answer the question, is there a linear combination that produces W using those 3 columns? The answer is yes.